your images. And in this case here we've got a loner, unpaired, not mapped to, but we don't care about that one. These three here are your image set, your range. Okay. Now with no many to ones, that means each of these elements in your target set or your codomain is mapped to either once, like here, 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 or not mapped at all. Okay? And that means that this mapping is what? Well, by definition, it's injective, right? That's what injective means. It means each element in your codomain, your target set, is mapped to, at most, once. Right? So it could be mapped to 0 times, so it's not mapped at all. And like, for example, this one here. Okay? So if that's true, it's injective. So we've proved that from the right-hand side to the left-hand side. Okay, now the other way, only if. Now, P is P only if Q. There's only one way you can get P, and that's by having Q. So if you do have P, you must have had Q. So if P, then Q. Right? I've done that many times. So basic, it's good to get this really unconscious almost under your belt. All right. So the only if case. So assume P and derive Q. So in other words, assume the left-hand side and derive, prove, deduce the right-hand side. Okay, it's injective. So we start with this. It's injective. And remember, injective means that each element gets mapped to once or not at all. Right? That's what injective means. Right? So we're trying to prove something like this. This is what we're trying to prove. Okay? So let's concentrate on this, which is what? It's the size of the image set, the size of the range. Okay. Now it's injective. So because if it's injective, if it's mapped, it's mapped to only one time. Okay. Now this f of x here, that's the image set. So it has this size of the image set doesn't care about this loner here, right? That's not in the image set. We're only interested in these, like these three, for example. They are in the image set. Okay. Now the ones that are in the image set are mapped to once, because it's an injective mapping, right? By definition, that's given. We're going from P to Q now. The only if part, if P then Q. So we're going from here to there. So we're trying to figure out what's the size of your range, your f of big X. Well, you look at your image set, and each member of that image set is mapped to once. Okay. And all of your members of your starting set have to be mapped. That's the definition of a function. You have to map every member of your starting set, otherwise it's not a function. So by definition. Okay? So so the size of your image set mapped to once, right, must include all the elements of your starting set, because they get mapped once, right? So one here will be one there, one here, one there. It's a one-to-one, right? So for each element in your image set, there's a corresponding element in your starting set. It's one-to-one. No many-to-one. Okay, so here's an example. We're using that concept again. No many-to-ones, right? So if it's one-to-one like that, therefore, the size of this image set is equal to the size of your starting set, which is this. Okay? So we've proved Q. Right? So we've proved 2, because we've now done it both ways. Okay. Now 3 is similar to 2. Yes, it's very similar reasoning. Well, but instead of injective, we're now told that F is surjective. Now, what does that mean, surjective? A bit of revision here. Surjective means that every element in your target set, your codomain, gets mapped to. There are no loners. Here's a loner here. Here's a loner, right? So this mapping F here, which creates a loner, it doesn't get mapped to. That function is not surjective, whereas this one is. The function here is, because each member gets mapped. The function here is not surjective, because this one here does not get mapped. It's a loner. And what's this one? Well, each member in your target set, your codomain, does get mapped. Okay, so this is surjective. So surjective, not surjective because of this loner, and this one not surjective because of this loner. All right. Okay. So F is surjective if and only if. So again, a double-barreled proof. We have to go both ways. If the size of your range or image set is equal to the size, now not of X this time, it's the size of Y, right? And what's Y? Y is your target set, right? Okay, so it's an if and only if. So again, we could call this P, and call this Q, just similar as here. So the if part, so that'll be from Q to P, so from the right hand side to the left hand side. Okay, so what do we know here? The size of the target set is equal to the size of your range, the image set, is equal to the size of your target set. Okay, so let's concentrate on that. What does that mean? So your target set is equal to the size, done it again. The size of your range, the size of your image set, is equal to the size of your target set. Okay, think about that. What does that imply? What can you deduce from that? So that also means there can be no many-to-ones, right? So like here's an example of a many-to-one, but the size here is 2 and the size there is 3. So if your size of your range is equal to the size of your target set, then it must be 1-to-1. Okay? Must be 1-to-1. And if it's 1-to-1, that means for each element in your target set, there's a so for each image, if you like, there's a corresponding element in your starting set, in your domain. Okay? Now, this here is the size of your target set, right? But it's equal to the size of your image set. Okay. So the number of the images is equal to the size of your target set. Right? Now an image, so these three, for example, that's the size of your Y, that's the size of your target set. And that size is equal to the size, the number of images. and you're told that the number of images is equal to the size of this. So it has to be like a one-to-one. You can't have any many-to-one. Okay? So if it's like one-to-one, that means then the size of your, yeah, it's one-to-one. Okay. So we're going this way. So each of these members from your target set is mapped to once. Each or every member of your target set Y is mapped to once. So that means it is surjective. Right? They're all mapped to. They're all mapped to. And that's the definition of surjective. Okay, so we've proven from right to left. Okay, now the other way. So if it's surjective, how do we prove this? So we start with surjective, we've got to go that way. Alright, surjective. Now if it's surjective, that means that every element in your target set, your codomain, is mapped to, by definition. That's what surjective means. Okay? And we have to prove that the size of your image set, your range, is actually the size of your target set. So let's concentrate on this. And we're told it's surjective. Okay? So each element is mapped to. Each element is mapped to. Okay. So each element is mapped to, and let's say the size of this is x. So let's say little m. So the size of x here, let's write it down here, is little m. It has m elements. Okay. Now it's surjective. So every element in Y is mapped to. Now we will have m of these arrows, if you like, coming out of x, coming out of your domain, right? It's because little m is the size of x, okay? And we're told it's we're now going this way, right? We're going from left to right. We're told it's surjective. So each one is mapped. Right? Let's see. Let's think a little. So it's mapped. Okay, so if it's surjective, you could have many to ones. Right? That's allowed. Surjective simply means that each element is mapped to. So if you look at diagram 2, and I've got a little reference here. So you're told it's surjective, and you have to prove this. Okay. Now, how many elements in Y? Well, that's this. Okay. You're told it's surjective, so every element gets mapped. Okay. So how many elements get mapped? Well, it's surjective, so the number of elements that get mapped is by definition the size of your range. Okay. So your size of f of x is going to be what? Well, it's surjective. So every element here is mapped. So how many elements in this y? Well, mod of y. Okay?